So this week we're going to be looking at electric potential energy and voltage and the relationship between those two, and we're going to be working on an example problem using the conservation of energy with the electric potential energy. But let's just do a quick review of some of the things that we've been looking at so far. So first of all, we have this equation for electric potential energy, where the electric potential energy is equal to a charge multiplied by V, which is the voltage. Now, I've mentioned this before, but voltage actually tends to go by a lot of different names. I can call it voltage, I can call it electric potential, I can just call it potential, but the main thing is that potential or electric potential is not the same as electric potential energy. Now, to try and avoid that confusion, I'll usually refer to this as voltage, but not everyone does that, so we need to be aware of that. So there is some strong analogs here between the equation for electric potential energy and the equation for the electric force, which is helping us to gives us some idea of what the voltage is. So if we understand this idea that the electric field is a field that's present around a charge, so for a positive charge, I'll have this electric field that's pointing away from it. Right, and then if I introduce a second charge into this space, right, it's giving me some idea about the direction and magnitude of the force that's being exerted on it. And then the same thing is going to be true on the other side with voltage, right? So if I have a positive charge that's hanging out in space, it's creating this voltage around it. And we can represent this with equipotential lines. We'll talk about this in more detail next week, right? But it's going to have a voltage around it, and it's giving me some idea of what the electric potential energy would be if I introduced another charge into that voltage. The main difference between these two, one of the main differences, is that voltage and electric potential energy are both scalars, and as we've been noting repeatedly, the electric force and the electric field are both vectors, and so we're interested in their direction. Right. The other thing that we can be thinking about with voltage, if I rearrange this equation, is that the voltage is the electric potential energy per charge. Right, so this is a way of telling us how much electric potential energy each charge would have. So this has applications in, for example, batteries. If you look at any battery, it's probably going to have a rating in volts, the units for voltage of volts. Right, so a standard AA battery is going to have 1.5 volts, and so that's telling me the amount of electric potential energy that's being stored in that battery for every charge that's in it. All right. Okay, so let's look at an example problem, and we're going to be focusing on using the conservation of energy with the electric potential energy. So I've got a proton with a speed of 2.0 times 10 to the 5th meters per second, and it's entering a region of space in which source charges have created an electric potential. For this problem, we don't actually care how many source charges they are, where they are, what they look like. We just know that there are some charges in the area that are creating this voltage. So what is the proton speed after it moves through a potential difference of a positive 100 volts? All right, so let's look at that first part first. I've got my knowns listed on the side here, right? So my initial speed, and then this change in voltage of 100 volts. So what we're saying is we're moving between 2 points, A and B, for example, and the difference between A and B as my proton moves from A to B is 100 volts. Now, what the specific value of the voltage is at A or B really doesn't matter, all right? So I could say the voltage is at A is 0 and at B it's 100, right? And that's going to give me a potential difference of 100. I could say that the voltage at A is 1,000,000, and I could say the voltage at B is 1,100,000 volts, and I'd still get the potential difference of 100, and that is the only thing that's really going to matter in this problem, all right? So I've got a proton, which is moving from A to B, and I'm looking for the speed. So I'm using the conservation of energy, and so let's start by defining our system to make sure that it's isolated. so that all of my forces are internal to the system. And so to do this, I need my proton, my object that's moving, and all the source charges. So that all of those source charges exerting forces on my proton, right, are all going to be internal to the system. Now, with this being true, my system is isolated. And so the conservation of energy applies. So I can say that the change to my total energy in my system is going to be equal to 0, which is the same as saying that the initial total energy is equal to the final total energy. And we just need to ask ourselves what types of energies are in the initial state and what types of energies are in the final state. So in the initial state, I know that it's moving, right? So that is kinetic energy. So I've got some sort of initial kinetic energy. And then we are going to have some sort of initial voltage, probably, right? And that initial voltage is going to come along with a initial electric potential energy. So for right now, I'm just going to write this down as the electric potential energy initially. And then in my final state, well, I'm looking for the speed after it moves through this potential difference, all right? So that's going to show up in my final kinetic energy. And then there's also going to be some sort of electric potential energy in the final state associated with that voltage. Right, I can take this one step further and expand these equations. So for the kinetic energy, we've got 1/2 mass times the speed initially squared plus the charge of my proton times the voltage at the initial state. And I can do the same thing for the other side. All right, so when I'm looking at this, all right, I know that the V final is what we're looking for, but we don't know everything right now. Okay, so we said the mass, right, and that's going to be the mass of the proton, and that's something that we don't have on our list of knowns, but it is something that we do know. All right, so the mass of the proton, which you can find on your equation sheet, is 1.67 times 10 to the negative 27th kilograms. All right, so that's good. We know that. We know the initial speed. And then we also want to know Q, the charge. And the charge in this case is going to be the charge of a proton. And so that's going to be that positive fundamental charge or fundamental constant, 1.6 times 10 to the minus 19th coulombs. All right, so I know the charge. And I don't exactly know V initial or what V final are individually, so we're going to have to deal with that. Let's check the rest of these off. Boom, boom, right? I don't know what the initial and the final voltage are, but I do know what the change is. So instead of having to worry about what they are in the initial and final states exactly, I could do one of two things. I could pick an initial and final value that have a difference of 100, that would do it just fine, or I can rearrange my equation so that I end up with final minus initial for the voltage, and I'm going to pick that second option. So I'm going to start rearranging this so that I've got the change in voltage in my equation rather than the initial and the final. All right, so I'm going to have and I can factor out the Q from these last two expressions. V final minus V initial is going to be that change in voltage. All right, and then last, all I need to do is solve for my unknown. All right, that last equation got a little bit sloppy, but I'm taking the square root of 1/2 mV initial squared minus 2 times Q times the change in voltage, all divided by the mass of that proton again. Alright, so I can plug my numbers in for my list of knowns into this equation, and it should give me my final speed. Right, and we'll just double check one more time that all of these are in base SI units, so meters per second, good, volts, good, kilograms, good, and coulombs, good. Right, so we can plug those knowns in right from our list, and that should give us our final answer. Right, and then the second part is asking for what the speed, the final speed will be if the proton is replaced by an electron. All right, and so if I'm looking at this, my initial speed is going to be the same. My change in voltage is going to be the same. The only things that are really going to change are the mass of the electron and the charge. And so I can use that different mass and charge in order to calculate what this answer would be. All right, so if there are any questions about this process, feel free to let me know, and good luck.